This is CVPR 602, Physiologic Assessment. Today we're going to talk about oxygen pressures, oxygen saturation, oxygen content, and then apply it into calculating oxygen delivery and consumption. And we're also going to finish up on the importance of SVO2, or mixed venous oxygen saturations. Much of this material can be found in the Darvik book in Chapter 2. So we are going to talk about the transportation of oxygen and oxygenated blood to the body tissues. But first, let's take a moment to review blood in its basic elements.
What is blood? Blood is actually a mixture of cells suspended in a slightly yellowish liquid called plasma. Plasma is made up mostly of water, but it also contains proteins, sugars, hormones, and salts. The three different types of cells you'll find in plasma are red blood cells, or erythrocytes, white blood cells, or leukocytes, and platelets, or thrombocytes. Red blood cells give the blood its color and make up 40 to 45% of your blood. They're round and look a little like a donut without the hole in the middle. Their main job is to carry oxygen to the other cells of the body and to take away the carbon dioxide as a waste product. Red blood cells only live 4 months, but healthy bone marrow produces 4 to 5 billion red cells every hour to keep replenishing the ones that wear out. White blood cells, on the other hand, are the body's defense system. They all fight infection from bacteria, viruses, all those nasty microbes that can cause disease. Whenever germs begin to infect your body, they send out a signal that the granulocyte recognizes. Just as soon as the granulocyte detects the signal, it begins its journey to the site of the infection. When at last they find the invader germ, they quickly move in for the kill, first attacking the invader and then eating it. Something else that is truly amazing is how the platelets work. Platelets are small pieces of cell material, or cytoplasm, whose job it is to plug holes in the vessel walls. So, say you're standing inside the blood vessel and looking at the tear in its wall. You'd see millions of platelets responding to the injury, throwing themselves over the cut. They stick to the wound's edges and to each other to form a plug that slows the loss of blood within 3 to 5 minutes. A platelet plug will last for only 24 to 72 hours because the platelets run out of energy and begin to fall apart. But as long as there is still an unhealed hole in the blood vessel wall, the clot will continue being formed, dissolved, and reformed to stop and prevent more bleeding from occurring. When the wound is completely healed by the new cells growing over it, the clot will be cleared away and blood will begin to flow through the vessel normally.
So now that you've reviewed that video on blood, let's specifically look at how oxygen is carried through the blood. Oxygen that diffuses from the lungs or from our membrane oxygenator into the blood is carried in 2 forms. Oxygen is carried in 2 forms in the blood. It's carried as it's dissolved in plasma. Dissolved in plasma. And when we measure a PO2, or the partial pressure of oxygen, it's that oxygen that is dissolved in plasma. Now, oxygen is also bound to hemoglobin. Hemoglobin is inside the erythrocyte, or the red blood cell. So, 2 ways that oxygen is carried in the blood. First way is dissolved in the plasma. Secondly, bound to hemoglobin. And both of these forms can be measured. Again, PO2 for dissolved in plasma, and SO2, the saturation of oxygen, is that amount which is bound to hemoglobin, the percent saturation of hemoglobin. We'll use this train analogy several times. Again, oxygen is added to the hemoglobin. Hemoglobin is represented by the boxcars here. We load up the boxcars by binding oxygen to hemoglobin. That's the SaO2, the saturation of arterial blood. Cardiac output is the engine which pulls these boxcars through and delivers oxygen to the tissue. And the amount of oxygen that is extracted by the tissue, the oxygen consumption, is represented globally as SVO2, or the mixed venous saturation, as it's coming back through the lungs. Again, all the boxcars are full here. One boxcar is empty. 25% of the oxygen was unloaded in the tissue, and that leaves us with an SVO2 of 75%. So let's talk about the oxygen loading side right here. Again, oxygen uptake begins in the lungs, or the oxygenator. So when I use lungs here, I'm also talking about our membrane oxygenator, or artificial lung. And again, just to reiterate, oxygen is carried in the blood two ways: dissolved, and this only represents 2 or 3% of the total amount of oxygen content that's in the blood. So we can dissolve a lot of oxygen in the blood, but it only represents 2% of the oxygen carrying capacity of the blood. Again, that is measured as the partial pressure of oxygen in millimeters of mercury. Most of the oxygen content of the blood is combined and bound with hemoglobin and represented by the saturation of the oxygen saturations. That's 98% of our oxygen carrying capacity is the hemoglobin. That's why the erythrocytes are so important. Oxygen saturation is a measurement of the amount of oxygen bound to hemoglobin, and that's measured in percent. Again, if you're talking about arterial blood, it's SaO2, or if you're talking about venous blood, it's SVO2. So hemoglobin, really important. We'll look at this in a second, but going back, hemoglobin consists of 4 heme groups. Each heme molecule can carry one oxygen molecule. And so we understand this equation, hemoglobin plus oxygen, and you have this bound state. So again, here's a picture of hemoglobin. You can see it consists of an alpha chain, a beta chain, another alpha chain, so 2 alpha and 2 beta chain. There's also an iron molecule within this, embedded in this structure, and it's the iron. You know, maybe you hear about someone who has anemia, which is a low red blood cell count, and they'll be given iron supplements. And the reason for that iron is that it is a vital part of this hemoglobin molecule. Iron is also what gives a characteristic coloring of the blood. Red blood cells give blood its red color, obviously, but the saturation level will change that color. When you start performing cardiopulmonary bypass, you will see that the oxygenated blood going in is bright red. The venous blood coming back is more desaturated, darker bluish hue to it. So hemoglobin plus oxygen, again, is the oxyhemoglobin binding site is very strong at the lungs. But this is an important stoichiometric number here. 1.36 mLs of oxygen is the amount 1 gram of hemoglobin can carry. This number 1.36 is going to pop up in some of our equations as we move our way through. So again, dissolved plasma, the PaO2 combined with the oxygen that's bound to hemoglobin, the SaO2, there is a relationship between those two elements, and it can be shown in this oxyhemoglobin dissociation curve. And there's a relationship between the PO2, the dissolved, and the SO2, the bound amount of oxygen. It's a sigmoid shape, and it reflects the optimal conditions that exist to facilitate oxygen loading in the lungs, and then again in the tissue level, oxygen unloading in the tissues. And so this is a typical oxyhemoglobin curve, this classic sigmoid shape. A couple things to note here is the steep part of the curve, and you can see the PO2 along the bottom, and the saturation of oxygen bound to hemoglobin in our y-axis. And you can see once you're above like 96% oxygen saturation, this curve flattens out considerably. So once we're up around 90 millimeters of mercury, we're just about maximally bound to hemoglobin. No matter how high we go on our PO2s, if we go up to 180 millimeters of mercury, we're still at about 100%. It's flattened out. Again, at 50% saturated, we have a PO2 of about 27 millimeters of mercury. So the hemoglobin and oxygen affinity is the strength of the bond between hemoglobin and oxygen. So normal PO2, P50, or the value, the PO2 where the value is 50%, is 27, and this is at some standard conditions, which is normal pH, normal CO2 levels, and normal temperature, and a normal 2,3 DPG. So this oxyhemoglobin dissociation curve can really, there's a couple of key points here we need to look at. Again, in arterial blood, large changes in PO2s result in small changes in SO2s. So again, once we get up here about 80 to 100 millimeters of mercury, no matter how much oxygen we dissolve into the plasma, it doesn't really change the saturation level. It's going to be 100%. But in venous blood, so down here, venous blood lives right here in this the sharp part of the curve. In venous blood, small changes in PO2 results in large changes in what would be SVO2. So small changes in PO2 result in really large changes in SO2. This is one of the reasons we pay such close attention to the mixed venous saturations, that every perfusionist in the country will measure the venous blood as it comes back to his venous reservoir and have an inline real-time SVO2, because we can really pick up quickly on changes in the oxygen balance. Of course, a number of things can move this curve around. This oxyhemoglobin dissociation curve is not a constant. Things can change it. Temperature, pH, PCO2, and 2,3 DPG, a byproduct of red blood metabolism. So when we look at this oxyhemoglobin dissociation curve, we talk about a left shift, moving the curve to the left, and that would the net result of that is an increase in affinity between the hemoglobin and the oxygen, and a right shift, where you move that curve to the right, that would result in a decrease in affinity. And there are things that can change that, and it can be somewhat intuitive. Things that make the oxygen hemoglobin bond tighter would be an increase in pH, a decrease in PCO2, a decrease in temperature, and a decrease in 2,3 DPG. So just think about that for a second. If the temperature goes down, that the oxygen hemoglobin bond becomes much tighter. As a result, the saturations of venous blood tend to be higher because oxygen unloading is inhibited. Right shifts, a decrease in pH, an increase in PCO2, an increase in temperature. These things will shift the curve to the right, making oxygen less tightly bound to hemoglobin and more easily unloaded. This makes perfect sense if you think about when our tissue beds need oxygen, the pH will tend to go down. The PCO2, a byproduct of metabolism, will tend to go up. If we're using our skeletal muscles, our temperature goes up. All these things will shift that curve to the right. Oxygen is needed in these conditions, and so it's kind of a nice relationship that it becomes more easily unloaded because of the decreased affinity hemoglobin has for oxygen. So let's look at a couple of normal levels here. Oxygen saturation, again, it's the ratio of oxygenated hemoglobin to the total amount of hemoglobin. It's always expressed in percent. And normal levels for arterial blood is somewhere 96 to 98%. For venous blood, 65 to 75% is a normal mixed venous saturation, oxygen saturation. So right away you can see that we only unload about 25% of the total amount of oxygen content in the blood, and the rest of that oxygen is there in reserve. It provides a mechanism for compensation should we need that. And again, on bypass, when you're on bypass and you see a falling venous saturation that you're monitoring in your venous line of your circuit, if you see that trending downward, that's a very early trigger that maybe the oxygen delivery is too low, maybe the oxygen consumption has gone up, and it gives us a chance to sort that out and make some adjustments before we get very desaturated blood. So the loading part, this would refer to the oxygen content and the oxygen capacity of the blood. The amount of oxygen, and we usually measure, we usually express oxygen content as CaO2, the oxygen content in the arterial blood. So the amount of oxygen in 100 mLs of blood, and that defines exactly how much oxygen is present in the blood. And the normal range is 17 to 20 vol%. So it's an unusual unit, but it's it's based on 100 mLs of blood and the percent the percent of that blood that's maximally saturated. So here's our equation, and I'm really sorry about that. Oxygen content equals the oxygen bound to hemoglobin plus the oxygen dissolved. Remember, oxygen is carried in the blood in two forms, bound to hemoglobin and dissolved in the plasma. So oxygen content will take both of these units, and we have to add both of these together. Again, that stoichiometric content, 1.36, is the amount of oxygen bound to 1 gram of hemoglobin. So let's use 1.36 times the hemoglobin, which is measured in blood, times the saturation of that blood. So that becomes the bound content. Now we have to add the dissolved content, and that is 0.0031 times the PO2. So you can kind of see that the dissolved portion of oxygen is much, much less than what we're going to find in the bound. Dissolved oxygen is oftentimes viewed as insignificant. Some people will take this right off the oxygen content. I would like you, for this class, to actually calculate that using dissolved oxygen. Remember, on bypass, we can manipulate PO2s pretty significantly, so this can be much higher than the normal room air PO2. Talk more about that in class. So in class, I'm going to give you some of these things to calculate. We'll calculate this. I'll just leave it up for a second. You're free to apply the equation that we just learned right here to actually solving some of these. Remember, hematocrit, the rule of thumb on hematocrit is hematocrit divided by 3 will equal your hemoglobin. So if you have a hematocrit of 30, and that's the only thing you don't have a hemoglobin, divide that by 3, which would be 10, and use that for your hemoglobin. So there's a couple of things here you can work through now if you'd like, before class, but we'll certainly look at these in class. The next thing we discuss is oxygen transport. So once we have the content of oxygen loaded up in these boxcars, then we have to combine that with cardiac output or pump output or your pump flow, and this is going to give us oxygen transport and oxygen delivery. And I'm going to use those words somewhat interchangeably. And that's the amount of oxygen pumped out of the heart to the body per minute. Per minute. So the value of adequacy of the cardiopulmonary unit to maintain oxygen delivery for oxidative metabolism. And our normal ranges are 900 to 1,000 mLs of O2 per minute. Now, I understand in Jeff's class, in our applications, we have talked about indexed oxygen delivery, and that is great. In this class, I'll probably be asking you for delivery, the total amount of delivery that hasn't been normalized to body surface area. And so this equation, the delivery of oxygen, cardiac output times the oxygen content, and then there's a factor 10 to reconcile the units. And again, you should be able to solve equations like this. Feel free to pause this screencast and work out an answer that we can discuss in class. Oxygen consumption. Again, we load the oxygen. We have an oxygen content that's being driven by cardiac output or our pump flow, but that's being delivered through the tissues, and some of that oxygen is being consumed by oxidative metabolism. And so we need to be able to calculate the oxygen consumption or extraction. So oxygen extraction is the total amount of oxygen consumed by the body per minute. And it's used in conjunction with oxygen transport to assess the balance between oxygen supply and demand. One of the really important things that you do as a perfusionist is to recognize when the oxygen delivery and oxygen demand become out of balance. When if you deliver not enough to create that balance. We attempt as a perfusionist, and we learned all about hemodynamics, but we're not pressurists, we're perfusionists, and so this is part of perfusion. Do we have a good balance between oxygen delivery and oxygen consumption? So the normal range is 200 to 290 mLs of oxygen per minute, and we can begin to look at this equation as taking the output times 10 times hemoglobin times 13, that 1.36. And we can simplify this equation just to the arterial oxygen saturation minus the venous oxygen saturation. And feel free to work through this calculation prior to class. So I'm going to give you a few questions like this. Determine the O2 content pre and post bypass. Another equation here. There's a lot of information here. Can you calculate oxygen delivery? I think you can. Let's prove it in class. Again, you should be able to take the data that you see here, sort out what data you need to calculate oxygen consumption or oxygen extraction, and provide me with an answer with the correct units. Again, it's about oxygen supply and oxygen demand. Oxygen supply, which is oxygen delivery, and oxygen demand, which is oxygen consumption. We're monitoring that all the time during bypass. We monitor oxygen demand with that SVO2, that mixed venous saturation. If that starts trending downward, we know the oxygen demand has gone up and the delivery is not keeping up with that demand because there's a compensatory mechanism. And so let's talk about some of those compensatory mechanisms to oxygen supply and demand. One of the compensatory mechanisms is an increase in cardiac output. We all understand that. When we begin to exercise, our heart rate goes up. Our body is adapting to an oxygen demand situation, and it is providing more delivery by a higher cardiac output. And that can occur for a number of reasons. Somebody who is anemic will have a higher heart rate because the train needs to go around the tracks faster because it's carrying less boxcars of oxygen. Or an increase in oxygen demand, for example, the exercise analogy. So that's one compensatory mechanism. Again, on bypass, when we see a venous saturation going down, we quickly begin to tweak the flow if we can. The other compensatory mechanism is an increase in extraction. So our body will extract more oxygen. We will unload more boxcars of oxygen. We will tap into that oxygen reserve, and we'll start seeing a larger arterial venous oxygen saturation difference. Physiologically, there's something called selective redistribution, and this occurs. This occurs when the oxygen supply is so low that the body begins to prioritize what organs need what oxygen is available the most, and of course, usually it's the brain will selectively be redistributed that oxygen. On bypass, it's less of a compensatory mechanism we have to worry about. So again, there are specific threats to the oxygen balance. An increase in oxygen consumption. I want you to think about that. If we're on bypass, what could increase the metabolic rate of the patient? What are those things that could increase the metabolic rate of the patient? I'm going to ask you about that in class. A decrease in hemoglobin. Well, what could cause a decrease in hemoglobin in a bypass patient? So we're running a case. What would cause the hemoglobin to go down during bypass? Think about that, please. A decrease in the oxygen saturation in our arterial line during bypass. It's another great question I'm going to ask you tomorrow. A decrease in cardiac output. What would a decrease in cardiac output on bypass be? And why? What would cause this in a bypass patient? So I want you to think about each one of these. Take some notes to bring to class, and we're gonna continue to brainstorm each one of these specific threats: an increase in oxygen consumption, a decrease in hemoglobin, a decrease in oxygen saturation of our arterial line on bypass, and a decrease in cardiac output during bypass. I'd like to talk to you about the SVO2. And again, this is a primary parameter. And if you go back to the standards and guidelines, it talks about this as being one of those things that helps drive us in terms of are we adequately perfusing the patient? This is one of the primary ones that we look at. It's not the only picture. It can mislead us at times, but a decrease in SVO2 must indicate the body is called upon its compensatory mechanism, a last line of defense, to preserve oxygen balance, and intervention may be appropriate. So on bypass, we use inline blood gas monitoring. Up in the sim lab, you will have inline blood gas monitoring. So it definitely improves our care significantly. There's a number of ways we can find venous saturations. The PA catheter is one if it has an oximetric probe on it. Unfortunately, during bypass with a heart empty, the PA catheter is not going to be a good source of during bypass SVO2, but it's good for definitely pre-bypass. These oximetric probes use reflection spectrophotometry, and on bypass we'll often have measurements, real-time saturations with hematocrit, There's a number of different devices out there that do that. This is the BioTrend still in use, but you can see there's a clip-on sensor on the venous line, and it's measured through an optical cuvette. It measures 76%. That's beautiful. 24% hematocrit and 99% saturation on the arterial line. So there's a number of devices out there that can do this. Some of the ones that we use most often in this country is a CDI 500. You will see that often on your clinical rotations. Here's the final question I'd like to ask you to think about is, what do you do when on bypass the SVO drops from 80% saturated to 60% over 5 minutes? So you're sitting up around bypass and you're seeing your SVO2 drop from 80 to 75 to 70 to 65 to 60. And this takes place slowly but surely over 5 minutes. You see the saturation of the venous blood, oxygen saturation of the venous blood going down. What are you thinking about, and what do you do when on bypass when this occurs? What are some of the things that could cause this? What are some of the things you could do about it based on your understanding of oxygen content, delivery, and consumption? Thanks, guys. I really look forward to this. We're starting to get into the really nitty-gritty of physiologic assessment on bypass, and I look forward to talking to you about this. We'll see you then. Bye-bye.